So, what I'm going to look at is something known as moments in action, where sometimes we have an angle. So, we've been looking at moments when the forces are up, down, making it turn an X, Y, Z or equilibrium. But what about if the force is at an angle? You could see the F over here and you see the lever arm. So, you know that moments is equal to force times by the perpendicular distance. But if it's at an angle, then that's not a perpendicular distance. So a crucial word is perpendicular. The distance needs to be the shortest distance from the pivot to the line along which the force acts. And that would be the perpendicular distance. So if we are looking at this image over there, you can see a distance over here. Okay, that's the distance, but that's not the shortest distance. The shortest distance is if the force is going upwards, we could continue the line of action of the force there. We could put it down over here, like you see. And the shortest distance from the pivot is where it hits the line of action perpendicular. Okay, in math, you work this out as a tangent when the tangent hits from the center of the circle to the tangent, the perpendicular distance, and that is the shortest distance. So the line of action of a force is an imaginary straight line extending. Okay, so it's extending through the force arrow in both directions. It goes upwards and it goes downwards. So let's look at this diagram in your textbook. So the pivot is at the actual nut. You see it marked at the letter P, that's the pivot. And the spanner has a length from here of 0.3 meters. And then you got the force 100. Now we could extend the line of action of the force in both directions like so. And we see a 45-degree angle. Now, they give you 0.21 as the perpendicular distance from the pivot to the line of action of the force. But what about if they didn't give us that actual value? If that was empty space over here? Well, luckily, what we could do is we could use trigonometry. And we know that sine is opposite over hypotenuse. So opposite the angle is O, and this is my hypotenuse. So I know that my angle is 45 degrees. My opposite is what I'm looking for. That's the perpendicular distance divided by my hypotenuse, which is 0.3. So this value right over there is going to be the opposite, which is going to be 0.3 times by sine 45. So the perpendicular distance, what we could write it as distance, and we could write it as like that, symbolizing perpendicular, is 0.21. That is how they got the 0.21. If I rub it out, that's how they got it initially. What you could also do is you could split the force into components. So if I extended this line over there, we know from mathematics that the opposite angle is 45 degrees. So this is the line of the force that we're interested in. What we could do is we could resolve it and we could find out the force, the perpendicular force over there, which is perpendicular to the 0.3 meters, that black line. So you know that red over there and the black over there, they're both perpendicular. So what we could do is we could actually resolve the force instead and then do it. It's up to you if you want to resolve the actual distance or you want to resolve it. But either way, the force has to be perpendicular or the distance has to be perpendicular. Well, it's not really the correct way of saying it, but don't worry about it. But yeah, you got to resolve it and get it perpendicular. You got to get the force perpendicular because once you get the force perpendicular, all of a sudden the force is now perpendicular to the actual pivot. So if I wanted to do this, I could have just done it as sine 45 times by 100, okay? And that would get me to 70.7 newtons. If I did 70.7 times by 0.3, so let me just times it by 70, I get roughly 200 Newton meters, okay? Let's just check it with this. If I did 0.21, use that distance, and I used 100 Newtons there, and times the 2, I'll get 210 Newton meters. Either way, I get the same moment. But they both, the forces and the distance need to be perpendicular. That is the main point. Now, something very interesting is if I did, for example, moments is equal to force times by L, okay, I could write sine theta. But why don't I write sine theta when it's perpendicular, when it's already 90 degrees? And that is because sine of 90 degrees is just the number one. So it's already force times by perpendicular distance is already. So you don't need to resolve. That's why if with your previous one, you get moments is equal to force times by distance. But if it's at 90 degrees, it's already going to be a 1. And if I had something that looked like this, let's go over here, yeah. And my force was in parallel to the pivot, right? Parallel. Sine of 180 degrees, just so you know, it's 0, which is true. If the force acted parallel, right? Parallel, then it would have just it wouldn't create a turning moment. So let's look at this. We got a support at the left end over there and a support at B over there. The distance between here, A to there, is 5 meters. There's a reaction force at A called R1, and there's a reaction force R2 at B, okay? And then we see at around about 2.5 meters, the bridge's weight acts, and that just shows us that the bridge's weight is uniform. So it acts through the center of mass. So for a uniform symmetrical beam, the center of mass is at the geometric midpoint. If it was non-uniform, it wouldn't be at the midpoint. So we have to take the moments from one place. We either take the moments from here or we take the moments from over there. And that is because by doing that, we either say R1 is equal, we could ignore the R1 effect or the R2 effect. We could ignore those reaction forces. We're not saying that the reaction forces are 0. It just means the moment at that particular point is 0 if we're saying that is the pivot. So let's say anti-clockwise is positive and clockwise is negative. So if I want to do the anti-clockwise, I'll get that distance over there, which is 5 meters times by R2. And if it's in equilibrium, I should minus this distance from R1 to the man, which is 800 newtons times by 1 meter. And also this one over here. So this one is the distance from R1 to the midpoint. And all of this should be equal to 0 Newton meters if it's in equilibrium. So R2 times by 5 is equal to 800 times by 1. And then you put bracket and plus 1,200 times by 2.5. So you got 2 is equal to 3,800. And then R2 is equal to 3,800 divided by 5. R2 is equal to 760 newtons. Now, we know that R1 and R2 should add up. So if I do R1 plus the R2, which is 760, should equal all the downward forces, which in this case is 200 newtons, 2,000, sorry. So R1 is just going to be the 2,000 minus the 760 newtons, which gives me to 1,240 newtons for R1. Now, a big question is why R1 is 1,240, but R2 is 760. You would think that they'll be both 1,000 each. If the downward forces are 2,000, you think it's like thing. Why is that the case? And that is because the person is very close to R1. So the force needs to, there's a reaction force over there to support, needs to be much greater than from R2. Now, if the person decides to move over there, the reaction force in R1 will actually begin to drop, whereas the reaction force in R2 is going to start to increase. Roundabout at when this person goes exactly in the middle, they will be both balanced over there, and each one will carry 1,000 newtons if the person goes directly in the middle. So we're told that this is a uniform shelf. So if it's a uniform shelf, that means the weight of the shelf will be right at the geometric middle, which is right at that point, and it's 900 newtons downwards. Now, we could take moments from A, or we could take moments from B. It's up to you, but you have to choose a pivot. I'll take the moments from A over here, and I'll go anti-clockwise is positive, clockwise is negative. So let's go with all of the anti-clockwise moments. Well, one of the anti-clockwise moments is 6 meters in that distance times by RB, and it should be balanced by all the anti-clockwise moments, which in one case is over here, 3 meters times by the weight of the shelf, which is 900, plus the other one, which is the weight of the crate, which is 600 newtons, and it's 4.5 meters away. So 6 RB ends up equaling 5,400 Newton meters. So RB, the reaction force at that, should be 5,400 minus divided by 6, which should be 900 newtons. Now, we know RA, they should be equal to all of the downward forces, which in this case is 900 plus that, which is going to be 1,500. So RA is going to be 1,500 minus the 900. A ends up equaling 600 newtons. So let's look at this question. 120 Newton force acts at the end of a 0.45 lever. So we got some type of pivot over there. We could just draw a triangle to symbolize a pivot. And then we got this is 0.45 meters. Okay, and then the force is 120 newtons. Now it could act downwards or it could act upwards, but I'm just going to make it act upwards, so 120 newtons, and then we're going to extend the line of action of the force, and then we're told that the angle between the lever, which is this, and the force, so this angle right over there, is 35 degrees. Now calculate the moment. So we know moment is force times by distance, but we need the perpendicular distance. So this angle also is 35, and I'm going to draw the perpendicular distance in the green. So we're looking for this, which I'll call an X. So this is O, this is H, and we know that sine is equal to opposite over hypotenuse. So sine of 35 degrees is the opposite X over hypotenuse, which is 0.45. So X is equal to 0.45 times by sine 35. So whatever that distance is, the perpendicular distance, we then need to times it by the force. So we just do 120 times by that X, which is all of this. So we're essentially what we're doing is 120 times by 0.45 times by sine 35. And what we get is 31 Newton meters. And that is my answer.